Okay, so today is the last day of signal processing, I hope. So Ryan just brought to my attention here that the syntax here is there is an error. So maybe when you were trying it, you did it already. So this should be Hanning window. That's why I'm zero padding it before, because for dot product you need to have two vectors of the same length. But anyway, let's recap where we started last time. We stopped last time, and that was time frequency representation. We looked at the chirp with linear frequency, so it starts from a frequency which is low, and then linearly it increases, goes from 100 to 10,000. And you saw that you can use short time Fourier transform to get this spectrogram, which shows you that this signal is non-stationary. So a signal which has similar frequency content with time is called stationary. If it doesn't, it's non-stationary, as you can see here. I don't know how many of you tried this. You got what you see here. So that was one of the signals that I gave you, the one which is called velocity, ultrasound something. And if you did the spectrogram, you saw that it looks something like that. So here we have time axis and here frequency axis. So if you want to think about it, if you collapse everything in the time direction, you are going to get the spectrum. And the other way around, if you collapse everything in the frequency direction, you are going to get the time signal. So here you can see how the frequency content is changing with time. And I also showed you that the representation from short Fourier transform has a lot to do with the size of the window. So size of the window matter a lot. So if you increase the size of the window, what do we see? What does this slide show? Can someone summarize what we discussed last time? What are we looking at? Someone brave? So as you are increasing the time window, you are of course losing resolution in time because you are taking a larger window. But then you are gaining resolution in the frequency domain. So if you look at the size of, let's say, one block along this direction, you see that it becomes smaller. So it is the smallest here, the largest here, and the time resolution is exactly reciprocal. Because the uncertainty principle of Heisenberg says that the time resolution times frequency resolution is constant. It's greater than some constant. And because of that, if you increase one, you lose resolution in the other and vice versa. This is important. This is important because if you are doing short time Fourier transform and you are choosing one time window, you may not get a good representation. You shouldn't give up. You have to try different time windows. It's also important because because it has motivated some other ways of doing time frequency representation. For example, one of my favorites is the so-called wavelet transform. Has anyone ever heard of wavelet transform at some point? So wavelet transform is kind of a smart way to get around this problem of resolution in short time Fourier transform. Let's see how does this work. The formulation is here. So you start with a function which is called in wavelet transform literature a mother wavelet. So you take a window. For example, what you see here is a Gaussian window, but it's not the Gaussian that you think about. It's a higher order. It's a derivative of the Gaussian window. So what you do with this is that you scale it and you translate it. So this parameter A here is the way you scale the mother wavelet. So you scale it at low frequencies. The wavelet, let's say, would look like this. And as you increase the frequency, your wavelet basically adjusts. It becomes narrower. And the way it gives you a time frequency representation is because it's also translating, and that is with the parameter B. I don't want to go through the details of this by any means. I just want you to see that the same signal of the previous slide here has a much better representation. You can see the two low frequency components, and you can also see that there are higher frequency components, and they are happening at certain times. Now, you can even notice as you are going towards higher frequencies, kind of your windows become narrower, and the frequency becomes, the frequency resolution becomes worse, which is okay. It would mean that for smaller frequencies, you have better resolution than for very high frequencies. So everything kind of makes sense. But you are also windowing the data. So you are still adding some artifacts to your signal. That's unavoidable. That's why that people typically choose a wavelet which looks similar to their signal. It's kind of a trial and error thing, believe it or not. So you kind of have to play with a few wavelets. And maybe you know that actually geophysicists came up with the idea of wavelet transform. That's why probably some of you know about it. So it is something that came out of practice. People wanted to analyze the data that they had, and they came up with this idea. There are other ways to do time frequency representation. If any of you is doing research which he thinks he can benefit from that, you should talk to me about it, because that's something I've worked on at some point in my life. For example, there is another transform which is called HHT, and that is Hilbert-Huang transform. This has some benefits. It's called Hilbert-Huang transform. And the Hilbert refers to Hilbert transform. Where did we see Hilbert transform before? In which context? The envelope, exactly. And Huang is the name of a person who came up with a decomposition way, empirical mode decomposition, EMD. So this transform also has some benefits, especially because it can give you the instantaneous frequency. Of course, there are some costs associated with that. I decided not to include this in the lecture just because we are not going to use it later on, but if anyone is interested, there are good references, especially if you think you are going to use it for your research. Just let me know, and there is even a book called Hilbert-Huang transform. I have it, you can borrow it. Anyways, so now we learned that signals are something which is changing with time. hopefully we all know how to make a spectrum, look at the amplitude and the phase. We learned about time frequency. So we close that chapter and look at something more important, not more important, very important, and that is noise. If you ever worked in a lab which collected any kind of signal, you would see that the signal is never perfect. It never looks like, as beautiful as you may want it to look. So what is the definition of noise? What do you define noise? You see here something that I have. What kind of noise is that? What I'm just showing you. That's kind of a white noise, the kind of noise that you may want to put in your bedroom to sleep better. Just random noise. If you want to create this in MATLAB, you can use the random function. It is, I think, just rand or randn. But I like to define noise of anything which we don't want in our signal. So it doesn't need to look like that. It can be anything else, and I'll show you some other examples. But this is a good one. This kind of noise normally comes from electronics, and you see it in the signal. So for example, if you look closer at the, this is the same signal that you all have, the velocity US. You see that in the beginning, it doesn't start very nicely. There is this up and down, and that's noise. Okay, there is one concept that we need to learn about noise, very important, and that's signal-to-noise ratio. Sometimes you see SNR, that's the abbreviation. Let me write it down. So that's signal-to-noise ratio. Now, this one has different definitions, but the standard definition is what I want to share with you today, and I expect you to learn, of course. Typically, in non-destructive testing, this is being described in decibel, and it's being calculated as, this is just decibel, so we have 10 times logarithm base 10 of the variance of the signal to the variance of the noise. So if you use amplitude, which sometimes people use, remember there are different types of amplitude. RMS amplitude, peak amplitude, peak-to-peak amplitude. If you use some sort of amplitude, then you may remember from calculus that, the 2 of the logarithm comes outside, so then you have 20 times the logarithm in base 10, the amplitude of signal to the amplitude of noise. So what does that mean? In either case, let's say if you use the variance, it means that you take a part of your signal where there is no useful information. Everything is noise. Hopefully there is a part of your signal which is just noise, background noise, whatever you have. And then you calculate the variance of that part. And you can also take some other parts of your signal, you can even get the whole thing, where you have signal and noise together. Most of the time the noise is all over the place. So then that would be the variance of signal you calculated, and then you can very easily divide one by the other. You don't need to exclude noise, so you could take this to be the entire signal. That doesn't matter. it's important that you report what you have used to calculate signal-to-noise ratio and be consistent. But basically, you are just doing that. If you have MATLAB open and the signal is already open and so on, you may want to actually calculate the signal-to-noise ratio for this signal, just very quickly. If you don't have it open and someone next to you has it open, just share one computer. If one of you is already warmed up and has the MATLAB on and has plotted the signal, it's easy. So, for example, you can take for the variance of the signal, you can just take the variance of the whole thing, whatever you have called it, and for the noise, then you want to just limit. I just call it signal. You just limit it to certain numbers. Let's say the first 500 points or 400 points, whatever, so that you are just including the noise. Very simple. It was helpful if you had the signals already saved somewhere.
I know this is maybe
Exactly.
I just want to see what's going on.
I mean, I just want you to become comfortable with getting these portions of the signal, just using MATLAB, especially if you are not familiar. It's very simple. And the command for variance in MATLAB is just var, which is simple. Now, you may later on for yourself try to calculate this with amplitude and see how much different it is. You're not going to get the same numbers if you use. So you don't separate. So sigma S includes signal and noise, both. Sigma N, in this case, the noise seems to be just in the beginning. So if you just take, for example, the first 400 points of your vector, then that is just noise. Do you agree?
What happens if it is
Then you cannot use it like that. If it is, normally this is not the case. So especially in MDT, it's never the case. So you always have something, and then the signal comes. So fortunately, we don't have this situation. You should show me. I forgot, to be honest. I don't know exactly. But I'm sure that it's not too bad. So you have looked at the homework? Yeah, I encourage everyone else in the class, especially those who take the class for credit, to look at the homework. Especially if you are not very handy with MATLAB. Based on my experience of previous time, it may take a little bit of time for some of you to do the problem. So it would be helpful if you look at it. So does anyone have a number? So I write it down.
Well, I just have a question. How do we determine which, I understand that we want to differentiate between the signal variance range and then noise variance range.
No, the signal can include noise. And typically it does.
Okay.
Because
That's why
this-
that larger.
Right. It can be, you will get a slightly different numbers if you take the whole thing or if you take just a portion, but it won't be a deal breaker. It won't be like it'll be the same kind of thing. Does anyone have a number? You may think why this is useful because a lot of times, let's say you want to compare the performance of two measurement systems on the same plot. That's how you do it. Or you increase the amplitude and you want to see how the signal to noise ratio changes. That's how you do it. So when I do this for the signal, I get about 1.4, and for the noise, I get about 4. So it should be much bigger. Okay, try it. So I get a signal to noise ratio of about 25 dB. Is that what? No one has this number? So you should just take the first as a noise. Because you are listening in contact, not to the last one. That's why. Don't worry. But you know how to calculate. Okay. You know how to calculate it. It's now depending on what you use as the window, the numbers may be a little bit different, but you get the idea. Someone asked what's the difference between using the variance or the amplitude. It's just another way to calculate signal to noise ratio. And here instead of 10 you will have 20 because this is a squared but this isn't. So that's it. It's simple. Okay, let's move from this. I think everyone has the idea how to do this. Now, as I told you, the noise could look different. To me, this signal is also noisy. What's wrong with it? there is a trend. There is it's linearly going upward. This happens a lot. If you ever measure anything, you have seen this before. So this is what we had before. If you compare just visually the frequency content of the noise part to the frequency content of the noise signal, can I say that the noise is of higher frequency than the signal? Is this clear for everyone? This is high frequency noise. Yes? I want to see in everyone's face that this is, it's important. But here, the trend that you see could be, imagine it could be a part of a really large wave, as if your signal is riding over a very, very large wave. In other words, we are dealing with a low frequency noise.
That can be because of grounding.
It can be because of grounding. It can be because you have some vibration in the system if you don't use a vibration isolation table. Yeah, it can be for no reason. You will never figure out. It just happens based on my experience. But you have it. And here also, so that's also has a low frequency noise. It's less obvious here. Look at this signal. Do you see a kind of a wave going through this signal, bringing it up and down? It's not as obvious as before that it's going upward, but you should be able to notice when you see your signal looking like that something is wrong. There is something else also wrong with even this signal here. This low frequency noise, this high frequency noise was not everything which was wrong here. What else is wrong? If this is the signal you collected, what would concern you a little bit? Chaz? Did you want to say something, Chaz? Exactly. It's kind of hidden, but look, your signal doesn't start from zero. That's a problem. There is a DC offset. That's also a very low frequency noise. In fact, it's having a component at frequency of 0. We talked about this before. So you have a DC offset. So, so this is high frequency noise. This is DC offset. And here we have what I would call low frequency noise. In general. And sometimes, as some of you mentioned, this when it looks very linear, meaning that when the frequency is really much lower than the frequency of your signal content, we call it also trend. Just the terminology. Is there any question about that? Yeah.
Not about that, but why would there be a DC offset reported in the signal in the first place?
If it's not well grounded, this happens rather very often. This is real measurement data.
In the main data as well, the dimension at some point, they may be small and
That looks to me as high frequency noise. That's like as if you have the high frequency noise, which is, yeah. Does it look different to you?
so like sometimes you may also have high frequency noise in the main.
Yeah, we have it here too.
Yeah.
Look, that's very deep.
That's also part of
That's high frequency noise. Yeah. But you cannot isolate that so you can isolate it from the beginning, because that's where you know that it's only noise. Yeah. Okay. Now this is all bad news. Some of you may be already discouraged, but the good news is there are ways to get rid of this noise. So let's first look at what I have here. There are functions which are called filters. This is by itself, you can have a full course about filters, a graduate even level class, but I try to give you some very important understanding of what these filters are. So let's learn a few terms here. Let's see what we are looking at. Well, there are 4 plots. All of them are spectra. The x-axis is frequency, and the y-axis is some sort of a spectral amplitude. Now, this one is called a low-pass filter. Think about it as a gate. Okay? So, it is like a gate which lets everything in which is smaller than this omega sub c. And it is symmetric with respect to 0. So actually, if you only look at half of it, would be good enough. But ideally, you can look at it this way. As a gate which lets frequencies which are smaller than omega c go through. And it doesn't let any frequency which is higher go through. That's why it is called low pass. Think about it a little bit. And this is called an ideal low pass filter, because as you can see, it is perfectly one from negative omega c to omega c, and then abruptly goes to 0. That makes it ideal. So if you see this for the first time, think about this term low pass a little bit. Make sure you understand why this is called low pass. Now, the opposite of low pass is high pass. Let's just look at the half, the positive half. This one is a gate which doesn't let the frequencies which are smaller than omega c go through, but you actually can go through if you are larger than omega c. Okay?
What happens at the value of omega c?
Let's talk about this. This is an idea. This is now just a concept. We are going to talk about this. Now, there are combination of these two. So you can just focus on one side of this, to the right hand side, just the positive. If you have a band pass filter, it means that all the omegas which are between omega A and omega B can go through, and outside nothing else can go through. And the the sister of that is something which is called the band stop filter, meaning that it lets omegas which are greater than omega B go through. It lets the one which are less than omega A go through, but it doesn't let any frequency between omega A and omega B go through. These terms are important, what each one of these means. Now, let this settle a little bit, especially again if you have never seen this. These terms can be a little bit tricky. Now, why do we call this ideal? Someone may say, perfect, I take a window in frequency domain which just looks like that, and you have learned how to apply a window. I've shown you that. I just apply that window, and then I go from frequency domain to the time domain, and voila, I have my filtered signal. The fact is, there is a big problem with that. Last time, we kind of talked about it a little bit. If you use just the boxcar window, which is completely like ideal, it looks ideal, you are going to get a lot of ripples in time domain, and in frequency domain you are going to get this kind of filter response. So you see there is a lot of ripples, and more importantly there is a shoot off at the location where you actually want to change. You want to put, let's say in this case you have a low pass filter, so it's going to have a shootout and it's going to go down. In the time domain, the impulse response has a lot of ripples. So if you apply any filter which is very sharp like that, it's going to introduce a lot of artifacts in your signal. So you don't want to do that. The good news is there are better options. Hamming window, for example, is a very nice, has a very nice spectral response. You can see how smooth it is, and in the time domain it also has less ripples. So because of that, we don't use ideal filters. We design the filters basically using a window which satisfies certain conditions. Now, I only focus here pretty much on what is called the finite impulse response filter. This term means that the impulse response can be represented by a finite number of coefficients. It takes a few classes in signal processing to understand exactly what is going on with filter design, but we don't need to in this class. I just want to show you what they mean and how you can implement it in MATLAB and use it for your data. But if you are more interested, for example, the textbook that I have taken signal processing classes when I was a graduate student, and for example, this is a good textbook. I think it's very simple to follow if you want to have more information. Now, how does it work? So, realizing that, let's look at this one first. Realizing that it's not possible to have, you don't want to have an ideal signal, you have to design your signal. There are a lot of different parameters, but what matters for us here is that you kind of design your filter such that, for example, here is a low pass filter, that your window passes through these blocks, as you can see here, and you have this band pass at the desired frequency. Okay, you can control all these other parameters if you want. One parameter that I want you to know is the order of the filter. So this parameter n is the order of the filter. I want you to understand what it does. It's the number of coefficients for the filter transfer function. The larger it is, the stricter the filter becomes. Compare the one you see for 41st order, and the other one, the order is 121. See what happens when you go from a lower order filter to a higher order. So they both have the same low pass frequency. The frequency that you're setting is the same. If you increase the order, it becomes more strict, meaning that you are not going to give the filter much freedom. But at the same time, this overshoot here becomes more severe, just very close to the frequency that you are interested in. In the old times, people also cared about the computation. The higher the order is, the more expensive your filter becomes. Nowadays, we do not care. You can go with higher order filters and you don't have to feel guilty about it. But this is one parameter that you need to care about. Okay. Now, did this answer your question? What happens? So basically that doesn't exist. You always have this transition. And yeah, depending on the order, you are you always have some. Now, one useful filter that you may want to look at is this FIR, finite impulse response filter in MATLAB. Let's see how this works. So you need to first build the coefficients for this filter. That's what you do first. You basically design your filter. Right. N is the order of the filter. Wn is the frequency, what we call the cutoff frequency. But this is normalized by Nyquist frequency, the way the MATLAB function works. And then you have to specify the type of the filter. That's why it's very important to understand what each filter is. You can have high, low, bandpass, bandstop. And whenever you set the order, remember these figures that I showed you. The larger the order is, the more strict. You will have some strange things happening at the transition always, and it becomes more time-consuming, a little bit more, even now. So sometimes you don't need to have a very strict filter. You don't need to go to 400. You don't need to. You can work with 2 or 3. Anyway, so this is all to design the filter. And then you apply the filter. With this function. If the filter is band stop or band pass, then you will have to give both limits for the bandwidth. So you will give something for the lower end and for the upper end. Okay? So now we are ready to try it. We can first start with the signal that you already have and you opened and you have looked at, and we start there. I'm just trying to check that I said everything I wanted to say. Again, if you have specific questions, I'll be happy to tell you a lot more about filtering, but for the purpose of the class, if you understand what it does, would be sufficient. Now, this is the velocity US, the one that you already opened if you were working on this. As you remember, it had a high frequency noise. What type of filter should I use then to filter the high frequency noise? A low pass filter. If you are just a beginner, you may confuse this a little bit, but don't worry. If you think about it a little bit, you don't. So try to do that and see what you are going to get. If it works. Try to see if this works and you can get rid of the high frequency noise. Just the cutoff frequency. So that is depending on the filter that you want. It is, yeah. Just look at the figure here. This is, sorry, I didn't went too deeply here. That's what it is. And if you have a bandpass filter like you have here, yeah, I forgot actually to show you that. So basically, when you want to design a filter, you have something like that. You have two cutoffs, and you kind of have to decide how many decibels you want to fall from where you want things to be constant, go down. And based on that, you kind of want to have a window which goes through, this. If you do like filter design like electrical engineers do, you kind of specify all of that. You want to know exactly over this how much you are fluctuating, how much you are going down, and how sharply you go depends on the owner. And these are then, instead of FC, you will have to FA, FT. So, there are tons of other filters. So one that I really like is the volume loss filter. That's not the final Anyone has filtered the signal? So what you see here, then I've plotted the signal and the filtered signal, and you see that the energy in the high frequency part is reduced. It's kind of fun to see. Maybe too much. Maybe for an electrical engineer, it may require all of this. So let's look at some other function. Anyone has filtered? I think it's one of my favorites. Let's see. You need to look at your spectrum and see what is the noise. What is the frequency of the noise that you want to get rid of? I haven't given you the experience. You will see it. If you wait a little bit for this one, I'll ask you to actually calculate it. No. This one I basically, the sampling frequency is 1 because I haven't given you the sampling frequency. So just try the different numbers and see how it is. So 0.1 means that, what does it mean? It means that you are low pass filtering everything. You have to check your relative frequency. This is your relative frequency. Okay, sampling frequency is 1. The sampling frequency is 1. What is the relative frequency? So when I say 0.1, what frequencies are we keeping? That's the order, that's the cutoff frequency, normalized or analysis frequency, and that's the type of the filter. So, one good question was, so where do we get this 0.1? What does that mean? Well, this is the cutoff frequency over Nyquist frequency. You always know what frequency you want to get rid of. That's something that's what you know. That's why you are filtering the signal, right? Here, I gave you, basically, I haven't given you the sampling frequency, so the sampling frequency is 1. So the cutoff frequency, the Nyquist, is 1/2. So this noise is basically larger than this value, which is 0.1 times 0.5. This is 0.5. You always know your cutoff frequency. That's why you want to filter the signal. Now, yeah. Could you please?
The filter is acting after the setup frequency.
The filter, it's not very sharp, so the filter does this. So some of the previous one and some of it's not going to go very sharp. So it's some of it before and after it kind of will be included.
So we are using a low pass filter.
Yeah.
All we can do is plot the tell that setup frequency. That will be enough for us. Plot the frequency domain till setup frequency.
So
We don't need
we don't need to filter.
other part.
We don't need to filter. So that's why I started here. If you do that, you are going to add a lot of artifacts. If you just cut very sharply, then it is so multiplication in the frequency domain is equivalent to convolution in the time domain. If you are just cutting the frequencies, which I agree with you, that would be the first thought to do, then you are adding a lot of kind of vibrations into your signal in the time domain. So you are actually changing your signal. In a lot of applications, you don't want to do that. Does it make sense? It was a good try. Oh, why do we learn this? So if you succeeded in filtering the signal, and if you plot the frequencies, you will see that if you look at the spectra, you see that the filtered one has much lower amplitude at higher frequencies. Something that you would notice is that you have still a very large amplitude at frequency 0, and this is because of the DC offset. How do we get rid of DC offset? What would you do? Yes.
Just subtract it from all the values at 0.
What? Tim, I didn't.
Maybe I'm not understanding that.
No, I'm just soliciting ideas to see what would you do. There are different things to do, but what would you do if now, let's say, we could get the high frequency noise out? I mean, this looks much better, much cleaner. Now my question is now, what do I do with the DC offset? What do we do? You could, but that's kind of an overkill. For just DC offset, what would you do? More experienced ones. Ideas.
Yeah, just subtract the offset from the initial value, right? And then it would shift all the wire.
How do you know the offset?
I look at 0 and then see where it's plotted on.
What if it's a little bit up and down? It's the right idea. So you can just subtract the mean of the signal. That's what we do. You subtract the mean of the signal. You can just try it. So whatever you have called your signal, just just subtract the mean from it. It wouldn't work like that. I think you need to multiply this by 1s of the size of your signal. Because that's just a number. I think it doesn't work if you just do it. This will remove the DC offset. Some people just in frequency domain just zero the first. For f equal to 0, if you just zero that, that will work too, because normally you don't care about that low frequency. You can just look at the frequency, the complex valued frequency transform. For f equal to 0, just make that 0, and then you use IFFT, which is inverse Fourier transform, to get your signal back. But that's kind of complicated. I think it's much better to work in. Did anyone try this? I think you do have these signals, LF noise and trend in on Canvas. If you have already downloaded them, you could also try to see that you can high pass filter. Did you check the DC offset? After this class, we won't talk about signal processing as much. From time to time, then when something comes up, we just use it.
Okay, I have to do
if you have LF noise, okay, so now let's go through the last slide, and then we can work on whatever you are working on. I can answer your questions. So the fact is we can also do filtering in time domain. You just saw one example. When we took the mean out, that's kind of a small filtering in time domain. Now, there are some very useful filters. One is what is called the moving average filter, which is the command is a smooth. In fact, it's a low-pass FIR filter, but the way we apply it, you can think about it as really having a moving average. So you are sliding an averaging function over the signal. So it kind of kills all the high frequency fluctuations. That's why it's a low pass filter. All you need to do is to specify the function, and you want to see how large this cart is that you are driving over the signal. So that would be the size, 20. And another useful command in MATLAB, which Ryan told me in some versions it's not available, is detrend. So if you use detrend, it takes away linear trend from the signal. So if you have linear or near linear noise, then you can get rid of it. Of course, it can be also used for DC removal, because that's also a horizontal line. There are some more sophisticated way to filter the signal in time domain. And for example, one is this discrete wavelet transform, where you decompose the signal into a number of components, and then you just remove some of them that you don't want, and you do the inverse, going back to the time domain. If you have a particular application, you can talk to me about it, but I decided not to include more details on this. We already spent 3 classes. But it's also possible to use some other filtering methods in time domain, which are not necessarily, they are not looking at, it's probably answering your question a little bit. They are not necessarily looking at one particular bandwidth. So let's say if you have machinery and you know that there is some other machinery which is doing, which is adding some noise into your signal, this may not have a separate, completely separate bandwidth, but the shape can be. Then you can do this kind of discrete wavelet transform. This is a family of different methods. And then you just remove those ones you don't like. And then you do an inverse. You go from frequency to time domain and you get rid of it. If anyone is interested in more advanced way of filtering, you can just let me know. Now,